There is another one which is also interesting, which we call deferred correction. What it does, there is an upstream, pure upstream, and then you sum up to that the difference between central differentiation and the upstream, and you leave this an explicit part in the equation. I will introduce a little bit here as a parenthesis. You know, everything which is implicit, of course, is in the matrix coefficients, which is, you know, it's in the matrix of your system, linear system. If it's explicit, it's in the right-hand side of the system. So it's the normally called B term in the right-hand side. And this goes to the right-hand side. You do its explicit part. You get the central differentiation, you subtract from the ups. This is the same. But this one, I keep implicit, and this one is explicit. But when there is convergence, this cancels with this one. At the end of the procedure, of the iterative process, this cancels with that. And you will have a devaluation of phi at the integration point as a central differential scheme. And we are going to see central differential scheme does not produce numerical diffusion. Central differential scheme produces numerical oscillation and not numerical diffusion. So this algorithm ends up with no numerical diffusion, but they may be prone some numerical oscillations, which is another error which comes from the approximation of the advection terms. You know? Well, it's written here what I just said. What I'm showing here really shows to us that there's a lot of schemes that were developed a long time in order to have a better solution, let's say, avoid numerical diffusion, trying to avoid numerical oscillation, which is what we want. Quick scheme is written, applied to hexa meshes only. This is because it requires that you have this. Hexa meshes in unstructured grids are similar, you know, to a Cartesian. And then quick scheme is not, in fact, a polynomial. See, you have phi in P, phi in E, phi in W, phi in P. So it's using these three. And you are going to calculate, let's say here or there, doesn't matter. But here is expressed phi at this integration point. Phi at this integration point, if it were only upwind, would be phi on P only. It wouldn't involve this one. It would involve in this one. But this approximation, you know, there's some importance for the upstream point, for the downstream point, and here is in general. This is the distance. Then see, here's, if you put theta equal to 1, this term drops out, and you will have an average, theta equals to 1, an average in phi P and phi E, which is the central differential scheme. So this scheme recovers pure UDS and pure second order, no? And recover the second order upwind. So the traditional quick is when theta is 1/8. This is traditional quick. But this is general. You can use it. But then, see, there's no physics on that. There's no physics on that. It's just a polynomial that you go through 3 points, and then you have an expression. But there is no physics on that. You are not balancing. When you do theta equal to 1/8, I'm asking you, how is the weight of the diffusion compared to the advection when you put theta 1/8? You don't know, because we are phi e is removing 1/8 of this one, and of course the p is the heaviest, but then also using this one in the front, in the downstream. So when you have upstream, only upstream, this is 8/8. There's nothing here and nothing here. Phi e is equal to phi p if it's pure upstream. So, okay? Normal upstream. Now when you are doing that, you're saying summing 3/8 of this value and minus 1/8 of this value. What I asked you is what that means. How much diffusion is embodied there when I put theta is equal to 1/8? You don't know. It's just a mathematical approximation, you know? It's just a mathematical approximation. Because normally all the interpolation functions that were deduced a long time in the research, they always trying to bring the physics to create the interpolation function. That's the point. Just mathematical stuff, you know, you don't know what that creates in your interpolation function. And then there is another method, let's say muscle scheme for general meshes. What does the muscle scheme? Defined in the integration point is theta times phi central differencing, and 1 minus theta versus phi second order upwind. So blends two schemes which are second order, because central differential scheme is second order. Second order upstream is second order. So you are blending two second order schemes. And this we already know what that means. And then you do that, so theta is some weighting that you are saying, give more importance to the upstream, second order upstream, less importance to the central differential scheme. What you are saying on that? You're saying, give more importance to the advection and less importance to the diffusion. So theta is equal to 1. He's saying this is a pure diffusive problem, because if theta is equal to 1, the calculation of phi at the integration point is the calculation using central differencing, which is suitable, which is very good for diffusion problem. So this theta is related to the weight that you want to give to the diffusion or the advection. You know? It's clear? And let's go through the last general topic that we want to discuss, which applies for cell center and also cell vertex, which is the numerical diffusion, numerical oscillation. This is the way, this is graphically the way they appear in your solution. If you are computing a pulse, you want to have it preserved. If you have numerical diffusion, that's what happens with your gradient, a smeared gradient. If you have numerical oscillation, that's what happens. You can capture a little bit better the gradient, but you have overshoots and undershoots in your solution, you know. And we will be discussing this a little bit more. Maybe, I don't know if it's already now. Yes. This is the same plot. Smearing of the gradient. This would be the numerical. You would like to be this solution, and the numerical solution is the red one, different from what you would expect to have. There are very well-known errors which attenuates the grades in the flow. Numerical diffusion does that. On the other hand, it stabilizes the solution, the procedure. It's a lot easier to get conversions and if you use upwind. Then again, why are you solving your equations? What is your problem? What is your engineering problem? Does it accept some smearing of the gradients, but you are interested in the overall solution that can help you solving your engineering problem? Then use upwind. So there's no strict rules that I always have to get a solution with second order or more. Such a rule doesn't exist in engineering. What you have to do is to analyze your problem, to see what you want, what you can do. If the gradients in some parts are not too important for you, but the overall solution, velocities, then, but you know what you are doing. That's important. The problem is when you go to run a software, you don't know this, and then appears some result, and you don't know if that result contains some errors that you can accept, that your engineering problem can accept or not. This is the problem. So don't keep in mind, in your mind, is that, and sometimes you see that written, that you have to have the second order, that and that and that. No. Numerical simulation can be helpful even without having numerical values on your solution. I always try to say that if you are computing the fluid flow in this room, it's not enough for you to do some very fine grid resolution at the wall, because you are not interested in calculating the gradient there. Then it will be the derivative, you will need very fine grid. But if you are concerned about the main flow in this room, that to see if it affects you, if it makes you uncomfortable sitting in some places, doesn't matter if the velocity is 2 meters per second or 2.3. You want to have the idea of the main flow. Then even the numerical values are not, you don't need to go through some very tough calculation in order to have some idea of the flow. So all is connected. The engineering problem with the numerical simulation. Don't do numerical simulation thinking that everything has to be 10⁻⁸ tolerance, everything has to be second order or higher, but keep your simulation connected to the engineering solution. No? So upwind does that, but stabilize your solution. You are happy because you get some results in your solution. It's there. No? If you have central difference in second order, sometimes you get nothing, because it oscillates and then doesn't come the solution. I'm not saying that to get solution is enough. No, I already talked. Keep connected with engineering. You remember, the interpolation functions is what introduces the errors in your solution. The interpolation function is the main source of errors in your solution. If you are able to give to your numerical method the interpolation function, which are the solution of your problem, there will be no errors at all. You will get the exact solution. You know, this is written right there somewhere. But if you are able to do the exact solution for your numerical method, you don't need to calculate, right? You already have the solution, of course. And then, this is a very important point I want to go through. With the mathematical point of view, and I would say another point of view, physical point of view, about numerical diffusion. Say, if you have a grid like that, if you expand using a Taylor series, phi in P is phi in E minus, and now you expand phi in E is phi in E plus, I'm going in the direction of X. Now if I work with these two, I will find that the value of phi in the integration point we have called E here will be central differential by second order. If you trying to have a upwind scheme which is to say that this is equal to that, then we will have some error here, which looks like a diffusion, because it's a gradient, and this is the diffusion coefficient. Density times velocity times dx here is a false diffusion coefficient. It is there, false diffusion coefficient. Then for a long time they all say numerical diffusion appears when you solve your problem using as interpolation function upwind. Then shows up this coefficient. Then it came another way to explain that, another vision of that. I'm calling here another point of view. Another point of view, and this I took from Tatankar's book, which shows a pulse problem. You have two streams of fluid. Phi is equal to 2 here, phi is equal to 1, and these two streams, they have any kind of diffusion. So phi cannot diffuse from the top part to the bottom part of this problem. And this is a one-dimensional problem. If you use upstream differential scheme, this is the equation. This is the partial differential equation. It's a one-dimensional direction problem. This is the partial differential equation. The integration gives that. If you use upstream, you will end up that phi in the front is the phi in the back. And then you are marching in X, always with the same value. The pulse is preserved. And you are using upstream. And then you have that which is the exact solution of the equation. So you are upstream, and you have upstream differential scheme without numerical diffusion. So how come? The mathematical point of view, mathematical view, says that if it's an upstream, there is a term there which is a diffusion, numerical diffusion. We just saw in the previous slide that if you apply upstream, remains one term in the approximation which is first order, it looks like in a diffusion. But now, it didn't show up here. Why is that? Then, let's change just the frame of reference. The same physical problem, the same pulse here. I divide phi is equal to 2, if phi equals 1. Our pulse is here. And here's the flow now. Here's the grid. Now, the problem has to be represented in a new frame of reference, 2D Cartesian. So this is the equation. This is the pure advection equation in Cartesian coordinates for 2D. Then you integrate, normal procedure, finite volume, and then you are using upstream. And then you have that phi is equal to phi p, phi double is equal to phi capital, phi small, phi, just upstream, pure, considering the coordinate axis, which results in that. Which means that the value will be depending on that, and that is clearly some diffusion there. The profile will look like that. Here's the profile. There is some diffusion. Here's our flow with phi is equal to 1. On the top, our flow with phi is equal to 2. And there is some smearing of the gradient, so diffusion. So how about this diffusion? It's not from physics, the diffusion here. It's not from physics. This physics has no diffusion. Partial differential equation has no diffusion. The reason is because inexact interpolation functions were employed, and not because of the grid alignment. And then I'm trying here to clear a little bit, because I saw many students, reporting that numerical diffusion exists because the grid is not aligned with the flow. What's happening here? The grid is not aligned with the flow. But this is true. But we need to add another phrase on that. The reason is because the grid is inclined with the flow, and we insisted to use one-dimensional interpolation functions for our interpolation function. This is the problem. It's inclined, but we insisted to use what is an inexact interpolation function. If an exact interpolation function were used, the solution will be exact. Doesn't matter the we incline. You can incline the grid the way you want. The question is, use the right interpolation function, then you will have the good solution. If you insist to have a 1D, and 1D for y, and 1D for x, upwind, and the problem is 2D, that's the wrong part. So just to think that the grid is inclined with the flow, then there is numerical diffusion, it's a wrong thinking. Because this happens if you are using an interpolation function which is not a good one. If you insist to keep 1D and 1D in a 2D problem, of course. But then I think you could understand. It's not the fact which is inclined. It's because of the interpolation function which is not good for the problem. If you use an exact interpolation function, the solution will be the exact solution. This is some remarks on that, because I have seen. There's some, we face some computational issues when we are, here we are, here. So what is really then numerical diffusion and discretization error? If you have inexact interpolation functions, so we are using an interpolation function, let's say for a 3D problem, using 1D interpolation functions for each direction. This is a non-exact, inexact interpolation functions. This will give you truncation errors. Those truncation errors, working in the advection terms, it can give you numerical diffusion or numerical oscillations. If your algorithm to deal with the advection terms is a dissipative one, it smears the gradient and then gives you numerical oscillation. If your algorithm used for advection terms is non-dissipative schemes like central differentiation scheme, then you have numerical oscillation. What you have to do, in fact, is to cut here, no? To cut the truncation errors. How do you do that? Using better and better interpolation functions, which really follows and describes the physics of the problem that you are solving, that you want to solve, you know? No? And then these two are the most important, the main errors that we have in a numerical solution, you know. But it is a truncation error, yes, you know. That refining the grid, but it is refining the grid will not help in avoiding numerical diffusion. If you refine the grid, you will get the exact solution if your algorithm is consistent. So telling that refine the grid doesn't help to reduce the truncation errors, it doesn't sound good. It really doesn't sound good, you know. This slide just says what I'm just remarked it to you. Another interpolation which is we are faced with is temporal interpolation. Temporal interpolation. And then remember the partial differential equation. I'm going to write. Remember this equation. I'm going to do that, which is read there. Remember our partial differential equation. Plus equal tau. I can write like that. And this term, it will be depending on what I will do with this right hand side here. So my transient term, my temporal term, it can be written like that: t plus delta t minus t, where n plus 1 minus n, just backward, first order in time. Or I can do that: n plus 1, n, and n minus 1. It's still written here. N plus 1, n, n minus 1. Using 3 levels. This is a second order in time. I made already some comments and remarks on that, you know, if you, in terms of time step. And this is what happens for the explicit, implicit, and fully implicit. When you do the right hand side as a function of n only, all time step, all time level, and then you have everything explicit, you know, because you throw everything of equation and you evaluate in the previous time level. So this is the explicit. The stencil here is like that. You have no connection. This is your unknown, right? Every unknown has its equation. And then you have several equations which makes a linear system. Or a bunch of equations in the explicit case. But in the explicit case, you have no connection between this, you want to calculate this one, as a function of the neighbors at the same time level. So this is explicit. What is in red here goes, the blue arrows, let's call them the coefficients, right? The coefficients which connect the points to the one that you are interested in calculating. So there is no coefficients in this red connecting, because this point is related everything with the previous time level. So there will be no matrix for this, okay? Matrix entries are the blue arrows which is inside the red ellipse. I try to do some kind of graphics to understand that. So of course we know that. Explicit, you go sweeping equation by equation, and this equation depends only the previous time level. The other equation, previous time level. So it's just a series of calculations in the explicit. The implicit already has some coefficients connecting P with E, P with W, and also from the bottom. So we have coefficients now in the matrix. So this is a linear system to be solved, because these coefficients are in the matrix, are implicit, and I have to solve a linear system. Here I don't have a linear system. Here is what I said. Sweeping, point by point, calculating the new phi for every grid. Here we have an implicit part already, but I still keep some explicit, which is from previous time level. In a fully implicit, all this, the weight of these errors goes to the matrix. So this is the fully implicit, which involves the neighbor values at the time you are calculating and the neighbor values at the previous level. Fully implicit, it involves only the neighbors at the time you are calculating. This error disappears. And of course, it's always connected. This cell is always connected with the proper cell at the previous time level, because it's a transient, of course, you know. It's the evolution of the transient. So this is the temporal interpolation. You can use first order in time, or you can use second order in time. Yeah? And rising. Another comment is also with respect to the solution. It can be, this is a very, let's say, we could explain one class about this, you know. This is not my idea here. Just remember that I'm always solving in the beginning of time, and in the beginning of time, when my problem starts, when my procedure starts, of course, if it's a real transient, if it's a true transient, I know everything what's happening this time, 0. the temperature is that, the velocity is that, so it's a physical condition that I have. And then I will evolve in time, calculating my solution, velocities, temperatures, and everything, in every time level. Doesn't matter if now is implicit, I will solve in this time level. And if I'm following some conditions, this is a real, true transient initial conditions, and I don't distort the transient, because you can distort the transient. Then you will have until you reach steady state there. You can go also in a distorted transient. You can distort the transient doing some estimates that you think will be closer to the solution, steady state the solution what you want. Of course, as close as you can give you the estimates in the beginning of the process, you will need less iteration to get the steady state. Then is the false transient or the distorted transient. And there is several ways to distort your transient. One is giving some good estimation in the beginning of the calculation. And the other one is working on the equations itself. Using different time steps for different equations, you are distorting the transient. And then it is a process that can help you to reach the steady state easily with less computer time, you know. But this is there's more discussion to be done on that. I just want to remember that you can follow a true transient, or you can follow a distorted transient if you are interested only in the steady state solution. Well, this was really some background and recalling of important aspects which I consider. We didn't go through, of course, then it will become the computational 1 course, but I want to put in this course, for completeness, as I said, some remembering interpolation function, all these things, because then we go through what cell center or the conventional finite volume does, the numericals that we just saw, how it is done now when it's cell center, and then later how it's done in the element-based finite volume. One thing that I forgot to tell you is that normally you leave the coordinate time in the equations. Even if you are going to solve a steady state problem, you don't drop the time from the equations. You keep them there because time is the best relaxation parameter that you have in your equations, because time is related with the physics, and the way the equations are solved iteratively, there's a lot to do with the physics, the way the variable changes, and time, you can tune up the time in order to have small time steps, so you are driving your solution smoothly and slowly, so more stable. When you want to have some steady state calculation, and then you say, I can put a time step equal to infinity because I'm going from my initial condition to my steady state solution, we know that it's not possible. Solving fluid mechanics problem because of the strong coupling of the equations, the influence of one equation in another one, and it's a kind of system which is not stable for any time step. So we have to go slowly in choosing the best time step. If you don't have the time there in your equation, if you drop the time, then you have to put a relaxation parameter. And putting a relaxation parameter this relaxation parameter, you are going to choose the relaxation parameter, let's say 0.1, 0.22, but there's no physics involved when you choose the relaxation parameter. But if you keep the time, you are able even to change the time step for each equation, because you are not interested in the transient solution. You are interested only in the steady state solution. So the way the solution travels in time doesn't matter. What you are looking for is the steady state solution. So you can change time for each equation, say momentum in X, Y, and Z, energy, but you also can change time in each cell of each equation. Of course, it is a kind of difficult for you to choose different time steps for different control volumes in each equation. But if you want, you can do that. And you know that if my equation, if my physical problems has some kind of behavior in that equation and the other one equation, you can choose the time step according to the physics. If one equation develops physically, one variable develops physically faster than the other one, you can choose the time step. So the recommendation is don't drop the time step, the time in your equation, even if you are going to use the scheme to get the steady state solution. So we could talk more about that. I'm just back to this slide because I forgot to remember that it's important to leave the time in the equation, because time is the best relaxation parameter that we have.